Hello everyone, in this video I'm going to go over the Solow Growth Model, which is one of the important growth models that is used in order to explain the factors affecting an economy to grow over the long run. So this type of model is not a model used to explain, for example, business cycles, because business cycles are a short-run analysis. This model is used in order to explain factors affecting an economy to grow over a long run, and by long run, there is no specific cutoff, but just you can say 5 years or more. The Solow Growth Model explains growth in an economy as being a factor of three important things. So there are three important factors here. Factor number one is the amount of savings in the economy, or you can call it saving rate because it's a certain percent out of your income. The second factor is the population growth. Okay, so the population growth is another factor affecting the economy to grow over the long run. And the third factor is technological change. So I'm going to sorry, my mistake. So the third factor is technological change. Okay. So we have 1, 2, 3 important factors. And those three components are the three components of a Solow growth model. And it's a model, it's an equation, right? And we're going to talk about each of these components in details. So the Solow growth model, first of all, assumes that we are talking about growth, or in other words, is the real GDP per worker. And this real GDP per worker is equal to A, where A here reflects the total factor productivity, and you also have F of K, which is a function of K. Okay, so in other words, K is the capital accumulation or the capital per worker. You can call it capital accumulation per worker, or can you call it capital per worker, or you can actually call it capital labor ratio. Okay, the total factor productivity, we will make the model simple at the beginning, and we assume that A is equal to 1. So A is just constant and it's equal to 1. So the simple version is basically Y depends or is a function of capital labor ratio. This is like this, the very simple version of the model. F is F of K, or a function of K, or a function of capital labor ratio. Okay, so this is like the very simple version of the model. And Y can also be written as consumption plus investment. So you already know from your principles of macro course that output actually depends on other things, but we are not going to talk about these other things. So you have this in your background that, let's put this as a note, that Y in the principles of macro was basically equal to C plus I plus government spending plus net exports, which is exports minus imports. So we're not talking about this now. We're making just a model that is very simple, that only depends on consumption and investment. All right, so the consumption here is the amount that is consumed of goods and services in the economy, and investment is basically when you go to a bank and you borrow funds. So this is the investment or the demand for funds. As you know that this demand for funds has to be equal to the supply of funds. So the supply is the savings. When you go to the bank, you put your savings, someone else is going to demand it, which are the investors. So from my point of view, if I go to the bank and save my money, then I'm going to be a saver or a supplier of funds, and someone else is going to demand it. So this person is demanding funds or investor. So it has to be the case that investment in equilibrium is equal to savings. So you can write it as capital S, or you can write it as a small s, which stands for a ratio, right? Out of income. So the big or the capital one, the capital letter S stands for an amount of savings, right? And the small letter s is basically the saving ratio out of income. So in other words, you can write it this way: investment, the amount of investment in the economy has to be equal to, like in equilibrium, the total amount of savings. Or I can write it this way: savings is equal to a certain ratio out of my output. So investment can be written as SY. Okay? So you can actually write this one. Let me just try to clean this part. And you can actually write this one as income is equal to consumption plus a small fraction of output. That's the same thing. Okay? You can also write it as this way. So can also write it this way. You can say that given that I can write y as fk, I can also rewrite this as c plus small s times a function of capital output ratio. Okay, you can call it capital per worker. You can call this one capital per worker, or you can call it the capital labor ratio, which is, as you know, it's a measure of the level of overall economic efficiency. Okay, so I'm assuming that you have read the chapter 6 of your textbook. So we reach this part where we are saying like output is equal to consumption plus investment, and we can write consumption as C, saving ratio, it's going to be a certain percent, out of output. To make this model, or to make this Solow model more of kind of expanding this model and to include other factors affecting, or to make the model more detailed, so we have to understand that in equilibrium, everything that you add has to have another force that is subtracting it, right? So you have positive that is equal to negative until you reach equilibrium. So you have a good example in your textbook talking about the change in the level of water, and the water flowing in has to be equal to the water flowing out. So that makes the change in water, or the change in water, equal to 0. That's exactly the same thing in adding and subtracting capital. So whatever is investing, or you're investing, you're taking out of your capital an amount of depreciation, such that the change in capital labor ratio is equal to 0. So you have a force that is adding, you have a force that is subtracting, both together makes the change equal to 0. So when we talk about this important variable, which is k, we want to know when is this k will stop moving, right? When the changes in k will stop moving. because when the change in K is equal to 0, we call this stage as the steady state. So you already know this from your textbook. So knowing when we can reach a steady state is like, you can think of it in micro like a break-even point, will tell us when the economy will stop moving. Any force that is adding is equal to the forces that is subtracting these funds out of the economy, so the economy will stop moving. So in order to know the steady state, we have to analyze what are the factors affecting capital labor ratio to change. So as you have in your textbook, we are talking about the change in capital output ratio is equal to the amount of people are adding as investment, I, minus the depreciation of this capital. So by over time, the machines will wear out and you will need to replace it. So there is a certain ratio of depreciation out of capital. Knowing that, on the previous slide, I think I wrote it as capital I, so I just want to keep the same notation. Okay, let me write it as capital I. In your textbook, it's just a small I, but I just want to keep the same notation I have on this explanation. Okay, so this is investment, this is depreciation ratio out of capital. Okay, so in order to know the change in capital labor ratio, right, we have two forces, and we can rewrite this one as investment. We already know it's equal to savings minus depreciation out of capital labor ratio. Or you can rewrite it as it's the small s out of the function of K, which is output, minus dK. We have a positive force on this side and we have a negative force on this side. The equilibrium between these two would make the change in capital equal to 0. So if the change in capital is equal to 0, this would imply that whatever I add in this economy is equal to whatever I subtract. And this is basically what we call the steady state. So in order to reach this steady state, you can compute this mathematically and try to find the equilibrium point between these two and say, okay, this is my steady state level of output, as I'm going to show in the example. Or you can have it graphically, and it's an intersection between this function and this function. So when you find the intersection between these two, then you will say this is the steady state. So it's either I'm going to give you like numbers and you need to compute it in order to find this equilibrium, or it's basically a graph and you want to find the intersection. Okay, so I'm going to stop here and I'm going to show you a mathematical example on the steady state.